We aim to learn about particle physics, but rather than doing this with classic collider, high energy, large scale experiments, we aim to do so by very accurately examining the structure of simple molecules. And the structure of these molecules is slightly altered by the same particles and effects that can be studied with colliders. And therefore, by accurately examining how they are changed, we can learn something about nature itself. We can benefit from atomic physics techniques of quantum control, preparation, and efficient state readout. And that together has made the field of molecule experiments a complementary avenue to the collider experiments. And in some directions, they can even exceed the precision that is attainable with collider experiments, helping to set the direction for a future collider. My thesis is about using the technique of laser cooling to improve the precision of our planned experiment to measure the electric dipole moment. And we need to do this because in order to benefit from the potential of neutral molecules, as in they're neutral, so you can fit many of them in a small volume, but you need to get them there. And so the source of molecules that we have produces a beam that's very diverted. So as it flies, it spreads out. And since our experiment is a few meters long, if it spreads out too much, the beam, then nothing is left at the end. So we need some mechanism to stop the beam from spreading. And that mechanism is laser cooling. So if our beam moves into the plane and we apply laser light from the sides, top and bottom, if we tune the color of this light just right, we can exert a force parallel to the direction of the laser light. And since the light is coming from all sides, this means that the molecules will feel a force opposing their motion in the transverse plane, which stops them spreading out. But because molecules are complex objects, they can vibrate, they can rotate. This all introduces various energy scales that we have to take into account if we want to scatter enough light of the cooling lasers in order to exert a measurable force. Or the complexity of the molecules translates to needing many different laser frequencies in order to have a sufficiently closed cycle that lets you scatter thousands of photons. So in the end, we need about 12 different colors of laser light in order to exert the cooling force. And then we need a few more frequencies to also accurately detect the molecules. We have a set of 4 lasers that we add several sidebands to. And in the end, we have to combine all of these beams, send them to the experiment, and make sure that the molecules see a constant, stable color of light as they fly through the experiment. This system did not exist when I started this laser system. So building that, fine-tuning it, improving it every now and then was an integral part of my work. While we now know in the first place that we can exert this force, so we can do the version of the experiment that we have in mind, but we've also identified several areas of improvement that will let us exert a significantly stronger force, which directly translates to a higher precision.